Alright, so all these machines are connected through the network. So the nodes in the rack are connected together with the Ethernet switch, which is connected to the master node through another switch. So to connect them, we're just using the standard network protocol, transmission control protocol, and Ethernet protocol. These are the protocols that we use for the internet. So they allow for connections between computers. So we establish a connection by opening a port and to a specific IP address. So the machine is identified through its IP address. And each machine will have a unique address and port. And through that port, the transmission control protocol can establish a connection from the sending to the receiving machine. So this is used for the clients to communicate with the name node and with the data nodes, and also for the data node to talk to the master or name node. We can run code through a remote procedure call. So remote procedure call is another protocol that can be used here. That allows us to call functions remotely through the network. So the master node, name node, is a server similar to the way web servers are. It's always sitting there and waiting for incoming connections to or requests from client machines. So the name node does not issue requests, it accepts requests from the data nodes and responds to any remote procedure calls or any requests that the data nodes and the clients make to it. They usually will make requests to ask where are the blocks of particular file, and or if new files are created, they're going to tell the name node what these files are and where the pieces are located. So we mentioned that failures are expected. So with this HDFS system, there is 3 points of failure that we can have. The first one is the name node can fail, which is the worst case scenario. Any of the data nodes can fail, and that happens often. And then we can have a part of the network become disconnected from the rest of the cluster. If that happens, the entire structure of the cluster is no longer connected to the rest of the cluster. How can we tell this? We already mentioned that these data nodes will send this heartbeat every 3 seconds because we want to make sure they're alive. So if a bunch of name nodes, we don't hear from them, then we know something is wrong with the network and an entire part of the cluster got disconnected. The name node will mark these data nodes and it does not send any more requests to them. And any data that was supposed to be obtained from the failed nodes, it's not available anymore, so we need to look for the copies of this data in the other nodes. We mentioned that each block is replicated 3 times. If we have a factor of replication 3, then obviously if some of the data nodes disappears, then we will no longer have 3 copies at each block. And if that happens, we need to create more copies. We might need to create more copies for other reasons. It is possible parts of the hard drive became corrupted, because remember, these are cheap, everyday use computers, and hard drives partially can fail. Some of the blocks can be lost because of that. Or because the data node is no longer available. It can be no longer available because it got disconnected from the network, or it can crash or hang or have a memory leak or some other problem. So that is expected. If that happens, we need to rebalance our cluster, so we need to find other places to keep copies of the missing blocks and recompute the network utilization to make sure we're not creating any network congestion in the new places that we're placing the missing blocks. So if it happens that some file has a very high demand or lots of client requests want this file, then we might need to create more copies of that and place them in other data nodes. And that's also an open research question, because that has not been implemented yet. We mentioned that we do keep a checksum. So the checksum is used in case the file gets corrupted during network transmission, because we can have interference, electromagnetic storms, or some other noise on the channel that's corrupted the data. And if that happens, we have this checksum that we can determine that there is an error and or try to correct the error. If not, we need to ask the client to resend this data packet, or go and look for other copies of it in another data node. And so we talked about network failure, data node failure, and we mentioned that the third type of failure could be just the master node or main node failed. And in that case, as you mentioned, we keep backups, so those log files is what is being backed up. The file system image and the edit log are the changes that was made to that particular file system image. So those are being backed up, and we keep several copies of them. And when we said that this particular file system is designed for streaming data, we mean the write it one time and read many times at streaming speeds. The block size, we said that is 64 megabytes. It is the optimal size is 128 megabytes. When they were trying to improve the seek time, and that came up to be the best size of the block. And again, this is much bigger than the block sizes in your laptops. Because we have huge files here, and they will not fit even into this kind of chunk, which does not usually happen on files on everyday laptops. So the file is chopped into 64 megabyte chunks and stored. Each one goes in its own block. So a staging or pipelining that we have seen earlier. The HDFS client caches the data into a temporary file, and when the data has reached HDFS block size, the client contacts the name node. The name node will insert the file name into its directory structure hierarchy, and it will allocate a data block for it. And then the name node will respond to the client with the identity of the data node where this block is supposed to be physically stored, and the client, and also where all the copies of this block should be stored. And then the client sends it from its local memory to the data node.